and I'd like to welcome you to today's webinar hosted by the Building America program. We are excited to have Andrew Porschke and Kota Weno joining us today to talk about strategies to improve the performance of heating, ventilating, and air conditioning systems for low-load homes and home performance retrofits. Larry Brand of the PARD team was unable to join us today. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side will display the telephone number and audio pin you should use to dial in. Panelists, we ask that you please mute your audio device while you are not presenting. If you have technical difficulties with the webinar, you may contact the GoToWebinars help desk at 888-259-3826 for assistance. If you would like to ask a question, please use the questions pane to type in your question. Please indicate which speaker you are addressing your question to. If you are having difficulty viewing the materials through the webinar portal, you may find PDF copies of the presentation at the website listed here, and you may follow along as our speakers present. Today's webinar is being recorded, and the recording will be available on the DOE YouTube channel within a few weeks. We have an exciting agenda prepared for you today that will focus on strategies to improve the performance of HVAC systems for low-load new homes and home performance retrofits. Before our speakers begin, I will provide a short overview of the Building America program. Following the presentations, we will have a question and answer session, closing remarks, and a brief survey. The U.S. Department of Energy's Building America program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for nearly 20 years. This world-class research program partners with industry to bring cutting-edge innovations and resources to market. Building America is supported by 10 industry research teams and 4 national labs. Each of these teams and labs partner with dozens of industry professionals, including builders, remodelers, manufacturers, and utilities. The best and the brightest in the residential buildings industry can be found here. Building America uses applied research to deliver building science solutions using a 4-step framework. These innovative solutions are tested in homes to develop proven case studies of success the market can point to. Building America provides the tools the building industry needs to ensure the innovations are applied correctly, always keeping an eye on energy performance, durability, quality, and affordability. The final step, infrastructure development, is the conduit to getting innovations to the marketplace. Building America research focuses on how the components of new and existing homes work together through systems integration. As the market changes and evolves, so has the direction of our research in order to add value and drive changes in performance across the building industry. In addition to technical challenges we have been addressing for decades, there is now a need to understand market transformation issues such as valuation of energy efficiency. In the nearly 20 years of Building America research, we have spearheaded combining ultra-high efficiency with high performance in both new and existing homes, and we are consistently achieving this challenging task. For example, in 1995, a typical home used 3 times more energy per square foot compared to today, and indoor air quality, comfort, and durability problems were common. Today, a home built to DOE Zero Energy Ready home specifications uses less than half the energy and is more comfortable, healthy, and durable. By 2030, Building America will demonstrate that new and existing homes can produce more energy than they use. Do you want to know more about these proven innovations born out of world-class research? The Building America Solution Center is your one-stop source for expert information on hundreds of high-performance construction topics, including air sealing and insulation, HVAC components, windows, indoor air quality, and much more. You can find it by the URL on your screen or by searching on Building America Solution Center. Also, the Building America website provides information about the program, the latest top innovations and case studies, and there You can also subscribe to the monthly newsletter. And now on to today's presentation. Our webinar today will focus on strategies to improve the performance of HVAC systems for low-load new homes and home performance retrofits. If you would like more detailed information about any of these efforts, or if you are interested in collaborating, please feel free to contact any of our presenters. Our first speaker today is Andrew Porschke, a Research Initiative Specialist at Ibicus. Andrew uses his expertise in sensors and monitoring hardware to design and implement remote data acquisition systems to monitor test buildings and analyze the performance of HVAC systems to calibrate transient thermal models. His work at Ibicus also includes new product innovation, testing products for manufacturers and evaluating new systems against established metrics. Andrew's presentation today poses the question of what is simple when it comes to space conditioning. He will review alternatives to centrally ducted furnaces with distribution to each room, discuss how these options maintain comfort, and explain topics to talk over with clients looking for simple and low-cost alternatives to a single furnace and ducts to each room. Next up is Kota Ueno, a Senior Associate at Building Science Corporation. At BSC, he conducts forensic field investigations, energy and hydrothermal modeling, building science research, and field testing. Today, Kota will discuss BSC's research on ductless heat pumps versus mini-splits in high-performance houses, often configured as a simplified distribution system, meaning one heat source per floor. BSC monitored 8 of these houses in Massachusetts from 2011 through 2014, and Kota will present analysis of the monitored data. With that, I'd like to welcome Andrew to start the presentation.
All right, thank you. I hope you all can hear me, and thank you again for your time today. Let's get started. So a brief overview of what I'll be talking about today. We'll start by, I guess, defining the problem and the challenges that we're facing with low-load homes and space conditioning. We'll talk a little bit about thermal comfort, and then we'll get into some of the solutions that we've investigated and talk about data from 2 case studies that we have, a cold climate unoccupied lab house and a hot climate occupied test house. So some of you may have seen this picture before. We've talked about, you know, as we're moving loads lower and lower in production homes, you know, the size of that load is reducing. But what isn't reducing is the overall square footage of these homes. So we see a house which, built to benchmark standards, might have been a 7-ton cooling load. And the new house is now a 3-ton cooling load. And what's important is that the total CFM, you know, has been reduced significantly, but the square footage hasn't. We've gone from 2,800 CFM in this benchmark old construction style down to just 1,200 CFM, but we still have to condition, you know, this very large house, and that presents a lot of challenges. You know, a lot of homes are built with floor plans which, you know, have a lot of rooms which are disjointed from the center of the house, and it can be a pretty significant challenge to condition all of those rooms. And so traditional air handlers, you know, might not be the best solution anymore to continuing to condition these low-load homes. So a little bit about comfort. The definition for comfort is probably best stated in ASHRAE's Standard 55, and there's a lot of technical details that go into defining comfort. But ultimately what it comes down to is that it's a subjective evaluation, that it's, you know, expressed as an individual satisfaction with the environment. And so it becomes, you know, as much as we'd like to define it in scientific terms, it can still be very difficult to define comfort. And so what we like to use often is ACA Manual RS as a rough guideline for establishing comfort, and the definition is that all of the rooms should be within 2 degrees Fahrenheit of the thermostat during the heating season and 3 degrees Fahrenheit during the cooling season. And to that sense, a homeowner can set their thermostat to whatever they feel is comfortable, and they should expect their entire house to have a uniform level of comfort. So let's talk a little bit about, just step back, system design and some of the challenges that are currently being faced by low-load homes. Something that's very significant, that's becomes more and more prevalent as the overall shell and enclosure load goes down, is the disparity between heating and cooling loads and the amount of airflow that's needed to satisfy that load. You know, in modern forced air systems, all of the load is satisfied by moving air from either a hot point or a cold point and moving it to all of the rooms within the house. So there's a lot of numbers on this chart, but I'd just like to point out that the difference between heating airflow and cooling airflow can be pretty significant. Sometimes it's half the value of one or the other. And so as a designer, people are often faced with the question, which airflow do you deliver? If you deliver, say, the greater amount of airflow during one season, you might under-condition or over-condition that space during the other season. So there's a challenge here that doesn't have a direct answer. But we'll try to discuss some of the ways around that. You know, and so the other challenge that we're faced with lower and lower airflows is mixing the air both in the zone and around the house. And here's just a little bit of CFD modeling we've done. And in the standard register case, you can see that there is some mixing, but what actually is happening here is you have a lot more stratification. And we've actually looked at a case with a much smaller register that results in a higher outlet velocity, and you can actually see that there is somewhat better mixing down into the room in that case. So same CFM, but you get better mixing. So you have to be very careful with your design in order to mix the space. And similar behavior is seen in the cooling mode, where we have, you know, again, a little bit more stratification with the standard register. The air just kind of spills out, whereas with a little bit of a higher velocity, you actually mix that room better. And that's something that, you know, a strategy we'd like to suggest when it comes to lower and lower loads. You know, but you know, it's not all that easy, because you do still have to be aware of the occupied zone, and diffuser placement is crucial. You can't have these increased velocities in the occupied zone, or you might end up with complaints about drafts. So diffuser placement is also very critical if you're using these systems. So some of the challenges that we're currently seeing, lower and lower loads have resulted in lower CFMs and potentially lower system runtime if the system is oversized. That reduced CFM means less velocity and throw, and in turn that results in less mixing both within a room and within the whole house. So we have a challenge here to continue to provide adequate comfort with working with a lot less air. And also on top of that, these load disparities between the winter and the summer also require better mixing and longer system run times in order to adequately condition those exterior rooms that could potentially be sun tempered. And we'll see this issue coming up in some of the data that we'll look at. And so that different CFM between summer and winter presents a challenge. You know, so what are you know, some solutions? What should we be thinking about? You know, again, as always, equipment selection is critical, and you know, total CFM is also critical, and you have to understand the impact that will have on mixing in the entire house. And so if you do use ducts, you know, it's necessary to design that correctly to get the CFM that you need in each outlet. And once that system has been designed and installed, you know, it's really necessary to verify that that is correct. that you're getting the required CFM, or else there's going to be problems with comfort. And something that we're finding more and more provides a good alternative is to look at these higher velocity systems and design your system to maintain something like 600 feet per minute out of the register in order to adequately mix that room, to get adequate throw. And along that line, it's also necessary to think about the register, to think about the outlet, and pick one which will provide adequate throw and mixing. You can't just use one register for the entire house, whatever is available. You really have to select that and change that depending on your CFM. And now let's talk some about the simplified systems that we're throwing into the mix here. Are we talking about simple ducts? Are we talking about no ducts at all? Simple controls, maybe a simple air handler. Let's look at a couple of the simplified systems we've studied. So one case is to use a limited number of duct runs, perhaps just duct runs to the bedrooms with a central air distribution system, taking a traditional system and scaling it back as much as possible. That's one thing we'll look at. Another case might be a single point of distribution with passive transfer to all of the rooms. If you have a single-story house, you might think about supplying all of the air to one central room, and if the house has a low enough load, you might actually keep all of the rooms comfortable by using one outlet. And if that's not sufficient, something else that we've looked at then is using active transfer fans between the zones. So if you have a number of bedrooms which are distant from the central air handler, we've looked at the effect of active transfer fans, which are forcing air to mix zone to zone. Again, that's crucial, is mixing air not only in a room, but from one room to another. And one other strategy we'll look at a little bit is mini-split heat pumps, and a case study in a hot climate where we used some mini-split heat pumps. All right, so the first case study we'll look at is the lab house that we have conducted research for a number of years in Pittsburgh. This is a cold climate, and the house is constructed to a very high efficiency standard. It's not quite passive house, but it is a very low air change per minute, 0.6, with very high levels of insulation in the exterior and the attic. So we've studied a number of different strategies in this house over the years, and we'll present some of the results from those different studies. I'll briefly mention them now and then go into a little more detail as we continue to talk. So we did a single point distribution strategy with 2 thermostats and 2 zones. And one outlet was located in the first floor, one outlet in the second floor. We also did a single point distribution strategy, the same setup with 2 outlets, one on the first floor, one on the second floor, and we looked at the impact of active transfer fans to try to improve some of the mixing between the zones. And finally, for this case study, we'll look at a scenario where we tried to limit the number of ducts as much as possible and in order to try to maintain comfort with this simplified system. So the first strategy we employed was the single point distribution with passive mixing between all of the zones. Now right here we have a floor plan of the first floor of the test house, and you can see the supply register was located in one room and the return was located in another. Now the first floor of this house had no real doors for the major zones, and so it was a rather open floor plan, and so it was rather effective at mixing air throughout that entire zone. So here is some data from that case. I'm just going to take a minute and try to explain this graphic a little bit. On the left side here, we have the temperature in the zone relative to the thermostat. And we've marked the comfort band that we use, plus or minus 2 degrees Fahrenheit, which is this gray band, and all of the rooms then are plotted, and we'll see sometimes they stay within that band, and sometimes they go beyond that comfort band. But this is the temperature of the room relative to the thermostat. And for context, we've also included the outdoor temperature and the temperature at the thermostat. You can see on this day, it was a cloudy day, and the temperature was around 20 degrees Fahrenheit. And so one of the things that we were studying during this case is the effect of a deep setback. If the homeowner had turned the thermostat back overnight and then turned it on, and we wanted to look at the impact of the response that morning. So you can see the system did not operate overnight and then kicked on in the morning, and some of the rooms became uncomfortable, and that's the result of that setback. However, throughout the remainder of the day, once it returned to steady state, those zones did fall back down into the comfort band, and that whole first floor was comfortable, supplied by a single outlet for all of the conditioning air. So, that setback response is still something, of a challenge. However, this does work for open floor plans. Now let's look at the second floor. We had a single outlet in the second floor, which was supplying all of the conditioning air into this central hallway, which is in blue. And then we looked at different cases. One case, we had the doors open, and we looked at the passive transfer into the rooms, and we looked at the impact that had on comfort. Then we looked at another case where we closed the doors and installed and ran these active transfer grills and looked at the impact of mixing in that case to see if it could maintain comfort. So the first case we're going to look at is the sunny day on the second floor with the doors open. And again, we're looking at the house returning from a very deep setback. So you see the room temperatures are well below the thermostat design temperature. And then what we have is once the system begins to operate, those temperatures, they elevate, and then they tend to go beyond what the thermostat is calling for. And so we're actually seeing, with doors open, a lot of the air mixing into some of the rooms and not as well into the other rooms. We have this pretty big disparity. So it started to work, but the strategy still didn't provide what we felt to be adequate comfort. So we looked at another case where the doors were closed, and we used the active transfer fans to try to mix those rooms. And again, this is a single outlet on that second floor hallway, and we have these 4 bedrooms that we're looking at the impact of the comfort. And so what we'll see here is that one of the bedrooms did tend to run a little bit colder than the rest. So that bedroom would be considered uncomfortable. However, the rest of the rooms did more or less stay within that boundary. So in this case, we got to say that it didn't meet the standard, but potentially, there could be increased CFM or something that would help this one bedroom maintain comfort. But again, the challenge that we continued to see here is that if you're not supplying conditioned air to individual rooms, we tended to see those rooms not maintain comfort. So let's look at a different case. That was a cold, cloudy case. Now let's look at a cold, sunny day. And what we see is the rooms which have a lot of southern glazing tended to overheat during the day. They weren't mixed well enough with the rest of the house. And so that solar heat gain presented some challenges. Now, these were unshaded windows, so it's possible that with using some shading devices, you may be able to maintain comfort in this case. So another case that we then looked at was to supply a very limited CFM to each of the rooms on more of a consistent basis and see if that, in effect, could condition the rooms without a full duct system. In this case, we used a very small diameter 2-inch pipe to deliver that air. And despite that continuous operation, we still saw problems during cold, sunny days with overheating, that it just wasn't mixing well enough. So this continues to be a problem that we're seeing, is houses that have a lot of glazing tend to overheat. And so there's different strategies you might be able to use, such as shading, that would help reduce this impact. And so then, as a reference point, we also looked at a case with a right-sized system supplying air to every room to see if that worked. We've looked at these simplified cases, and sometimes it does work, sometimes it doesn't, and we want to see now the impact of a traditional system. So this is the second floor, doors closed, and we see this similar problem where on a sunny day we have overheating in those sun-tempered bedrooms that don't have a thermostat in them, and they're not thermally connected to the rest of the house very well because the doors are closed. And during this period, the system did not run at all because the thermostat was satisfied, but we didn't have mixing through this period. And so some things that impact this are the conduction between different rooms. Potentially, if there were ways to improve the conduction between rooms, that could help mitigate this problem. A lot of the results were heavily impacted by the location of that supply register. And that single point of distribution, if it was blowing into one of these rooms, that room could potentially overheat or be undercooled while the other rooms were not. And the other most significant driver in this house was the impact of solar heat gain. So the front of the house faced due south. So the bedroom in the bottom corner saw the most significant impact of the solar heat gains, as well as this western bedroom. As we saw, those rooms tended to overheat when the rest of the house stayed comfortable. So the challenge still is you have to mix the whole house if you want to maintain comfort. So let's look at a little bit of hot weather data. So again, now we're back to the first floor. This is the open floor plan, and we had that single point of distribution centrally on that first floor. And again, let's focus on the comfort band, which is this gray band here. We see that all of the room temperatures stay within that boundary during this period, and even during a period of pretty extensive system runtime. So, this works again quite well, even in the summer, for an open floor plan. Now let's look at the second floor. Whenever there's no sun tempering, those rooms do stay within that comfort band, but as soon as we see the impact of the solar heat gain, again we're seeing this overheating, even in the summer. And so let's look then at the right size system during the summer. Here on the first floor, it did maintain pretty adequate comfort. But again, on the second floor, even the right size system struggled to keep up with these solar heat gains. The system is running through this period, but there's not adequate mixing through those rooms. That is key. In order to maintain comfort in those rooms, you really need adequate mixing. So let's move on now to the other case study we're going to talk about. We have a hot, humid climate and an occupied test house. This house is built to Zero Energy Ready Home specifications, and with the conditioning strategy that we implemented was to use a combination of ductless and ducted mini-split heat pumps. So the floor plan of this house was a 5-bedroom home. So we had a number of rooms that were disjointed from the center of the house. And so as a result, we used a number of heat pump units. On the second floor, we had one ducted unit which supplied several of the bedrooms, and 2 ductless units, one for the central game room and one for a guest suite. And what we'll see here is that the guest suite you're able to actually turn off or turn on that zone depending on its occupancy and see energy savings because of that. On the first floor, we had a central unit which supplied the main living spaces. This is, again, a ductless head unit, and then another ductless unit in the front area. The master suite was located on the first floor and kind of central in the house, and it had a ducted unit to supply the couple of rooms in that suite. So this is some preliminary data from this year that we've been collecting on an ongoing basis, and we'd like to share some of those preliminary results with you. During the winter in this house, it was actually unoccupied at this point, and however, the systems were on and running, so we have some data that we can start to draw some conclusions. And so what you see here is actually the guest suite, which was set to a different temperature, and it is, so that's why it's at this elevated temperature. Now, the rest of the rooms did maintain a pretty tight grouping within their zone. So we have something on the order of a 4-degree temperature difference between the hottest and coldest room. However, the individual zones did maintain a very tight temperature clumping during this period. Now, it was unoccupied, the doors were open, but it did seem to be effective in this case. So now we have some data from the summer, and during this period the house was occupied, and it was we're looking at a number of very hot days here. And so, as I mentioned before, that guest suite, you can see, is drifting above the rest of the house. During this period, the mini-split heat pump in that room was turned off. So the occupants were able to have complete control over those rooms. And then looking at the rest of the data, we see other rooms which were on similar set points. We see them clumped very close together. They were well within that 3-degree temperature band if you look at the individual rooms which were on different set points. So this strategy seems to be quite effective in this case. So some of the conclusions that we can draw here are that large open spaces can be effectively conditioned from these simplified systems. But it's crucial that you have the correct placement and the correct register selection for that single point of distribution. Is it ready for every house out there? Certainly not, and that's something that we've found through this testing, and we found some potential ways to help improve those cases when it did not work correctly. Something else that we've found is that set up and set back can be hard to do uniformly. If you have a period where, say, the occupant is on vacation and they've turned off the system and all of the rooms of the house have been able to drift apart, whenever that system kicks back on, it's difficult to get all of the rooms back into a uniform temperature through that operation. And it's, the biggest challenge still is conditioning the furthest rooms from the set point, or from the thermostat, and they still need direct conditioned air. It's not adequate enough to have some of these passive mechanisms to condition those rooms. If you want to maintain and guarantee comfort, you still have to condition some rooms, but then you can simplify things in other rooms. And something that we've found, and that will be discussed in much greater detail in the next presentation, is that mini-split heat pumps, both ducted and ductless, using a combination of those, offer a very compelling alternative to the traditionally ducted systems. And they also provide the homeowner with a greater level of control over the specific set point and the specific operation. So that's it. My email is here. We'd like to acknowledge SNA Homes and Imagine Homes. SNA Homes was the builder of the Pittsburgh Lab House, and Imagine Homes for the hot and humid climate test house. I've also got links to some of the reports which we've written on these homes if you have further questions.
Thank you, Andrew. Next up is Coda Bueno.
Am I unmuted? Okay, I'm unmuted now. Okay, this is Coda Bueno. I'm going to be doing a presentation on the research that we did on with mini-split heat pumps operating in heating and cooling mode in a bunch of houses located in the Northeast in Massachusetts. So just jumping into my presentation here with a little bit of background. So we spent a lot of time working with a builder known as Transformations, Inc. Their shtick is they have been building net zero houses throughout Massachusetts in a variety of configurations. They've been doing this as their production basis housing for a bunch of years at this point. Part of their mix of strategies is to use these mini split heat pumps, these non-ducted heads mounted on walls, as part of their trade-off packages of doing more investment in the building shell or enclosure, and then using a simpler or lower cost space heating, space conditioning system. What they've been doing is they've put a single point of heating or cooling on each floor, typically on a two-story house. And this study examined the temperatures throughout the house, throughout a variety of operating conditions, and the energy use of these mini-split heat pumps. So just to take a quick step back, this is only the half-hour presentation version of this gigantic 140-page brick of a report that we all suffered through here. So this presentation is an overview. The report has all the details. It's currently in final review and will be released very shortly. So please, if you're frantically taking notes and screenshots, relax. You can watch the screen, listen, absorb, please. So the type of enclosure or shell that Transformation uses, shown in some of these figures. The walls are double stud, 12 inches thick, with 12 inches of low-density open-cell spray foam. The roof is well-sealed, air-sealed, and then vented attic with 1.5 feet of cellulose, R60 plus, well north of R60. Going down to the basement, closed cell foam, typical application on the walls, R20-ish, and R10 foam underneath the slab. The standard product uses triple glazed windows, U in the 0.2 range, and they're hitting 1 ACH 50 typically. So a bit more about mini split heat pumps. This type of product has been available and been in use in Asia and Europe for over 40 years. It's a very common technology. It has since come to North America and is just getting greater and greater acceptance into the marketplace. Now, one warning about mini split heat pumps, if you're comparing them with a standard ducted split system, the equipment is more expensive on a per ton basis, per 12,000 BTUs. But if we're talking about replacing a ducted system with a ductless system, you can actually gain significant savings because a lot of the installed cost of the split system is the sheet metal or the duct distribution system. In this study, we used equipment from Mitsubishi. There are a couple of other manufacturers that have some fantastic low temperature performance, which is critical if we're talking about relying on these heat pumps as the sole source of heating in a cooling climate like Zone 5, Massachusetts. So they retain their full heating capacity at a outdoor temperature of -5 degrees. They're rated down to -13, and some other practitioners that I've met, have had them operating down to -20. And note this is a specific type of equipment from a certain manufacturer. Other manufacturers do have equipment that can run down to this level. Another nice thing about mini splits is that they modulate to meet load. Basically, they ramp their fan speeds and compressor speeds up and down based on how much load they're facing, what the outdoor conditions and indoor conditions are. One thing that's found if you look at the ratings is that the best performance you can get out of these units is at part load, and they're the worst at full load. Basically, if they're chugging along at full load, they're at their lowest efficiency point. But that being said, several practitioners have examined this problem, and in cold wintertime conditions, they were showing COPs, or coefficients of performance, in the 2.5 to 3 range, which is actually excellent for a heat pump. COP, of course, is the ratio of how much energy out of the heat pump you get versus the amount of energy you're putting in using electricity. So the builder's experience with these mini-split heat pumps. Transformations build very low load houses in the 10 to 18,000 BTU per hour heating design load range. So this is well below what even the smallest furnaces out there are. The smallest furnaces I've seen are 40,000, maybe they modulate down to 30,000. All of their production uses these mini-split heat pumps as the single source of heating with no backup. Typically 1 per floor, so 2 for a 1,800 square foot 2-story house. So like I said before, he's taking the savings from the mechanicals and putting it back into the enclosure. So just as a ballpark cost, the cost of all those enclosure upgrades that I mentioned before, probably about $15,000 for a standard size house, and about $5,000 in savings on using this type of a simplified mechanical system. And what the builder's experience has been so far is that, very trouble-free operation. It's very reliable, very few callbacks, and when he has had a callback, it's typically something incredibly dumb, like the HVAC installer forgot to completely plumb the condensate line or something like that. By the way, point of information, you're looking at that lower left-hand image. You'll notice that the mini-split head is mounted on a small sheet of drywall. This is actually done so that the installer can come install all of the equipment in a single shot, just one trip to the job site, and then later on they finish the rough-in of electrical, other mechanicals, and then insulate and drywall around that. So, an overview of this monitoring project. The bulk of the projects, the houses we looked at, are these 8 houses located in 2 subdivisions in Massachusetts. There's a mix of monitoring packages in each of them. Some of them had, temperature RH sensors throughout. Others of them had, also added sensors which would tell the status of the door, open or closed, which actually has a significant effect on this type of simplified space conditioning problem, as well as power use of the mini-splits. You can see that these houses were monitored over various periods of time, some of them much less data than the others. The longest one was well over 2 years. The shortest one was shortest few were a little bit under a year. And you can also see that we went through some, both mild winters as well as some pretty severe winters, well north of the standard type of heating degree days we would see. Just showing some pictures of the monitoring packages. We would mount temperature relative humidity sensors on the walls in a couple of locations throughout the house. Log mini-split heat pump energy use on a 5-minute basis from the power panel. And the door open and close status would be done with a small data logger that has a reed switch that detects proximity to a magnet mounted on the door frame. And so you can tell when the door was closed. Unfortunately, the system does not actually tell you whether the door is fully closed, partially closed, or, well, it does not give you, give you an indication of how closed the door is. It only gives you an open or closed. So it's entirely possible that the open signals are also partially closed. Just shows an image of what a typical monitoring package setup might look like. This shows one of the smaller houses, the attached garage in the first floor, showing the mini-split heat pump over in the living room, the largest space, blowing into that space. And there are 2 temperature relative humidity sensors shown by these 2 green dots in 2 locations on the first floor. On the second floor, there was similarly 2 temperature RH sensors, as well as those door closure sensors on the 2 bedrooms, the places where doors were expected to be closed for extended periods. Okay, so we're going to look a little bit at the monitoring data that we had. And the first thing I'm going to do is just a little bit of an overview of the type of operating patterns we saw in the data, just so you have an understanding of this is the type of data that we collected, and this is the kind of thing that we can learn out of it. So this shows a typical plot that I use to show temperature and power use in these houses. So the orange is outdoor temperature. This is a chunk of winter from November through May. And the remaining traces are indoor temperatures. You can see they all fall within a pretty narrow band, most of them in the 65 to 70 range, some excursions, but they're mostly tracking together for the most part. But the other thing that we did monitor was the mini-split heat pump energy use. So what those blue dots show are the hourly energy use for the mini-split heat pump. That is graphed on the right-hand side, shows, this is 1,000 watts in average draw per hour, 2,000 watts for 1 hour. And what you can glean out of this is you can see towards the beginning of the winter, things got colder and colder. They realized, I guess it's time to turn on the heating system, So you can see that they slammed the heating system into gear. It ran for a bunch of hours at pretty high load. The maximum load for these systems is about 2,000 watts. And you can see that it just kind of chugs along, very few hours at zero. It just kind of modulates up and down based on outdoor temperature, how hard it is running. So you can see at these various points where it gets noticeably colder that you have a fair amount more electrical draw from your mini-split heat pump. This adds the blue data was for the first floor unit. The red data over here shows the second floor unit. You can see that it runs a little bit less, but a similar type of patterns running, cycling up and down. So if you also look at the 5-minute data, you can determine that this equipment actually is definitely modulating. It, very few hours running at zero. It does not, slam into gear and then shut off. It just ramps up and down based on the temperature. And also that comparison between the first and second floor, you can see that the first floor is really doing the heavy lifting on the heating side. Moving on to a plot of the cooling side, you can see a similar type of behavior where, for instance, over here, we had a couple of hot days. They realized it's time to turn on the air conditioner, and they turned on both units. Most of the indoor rooms are tracking pretty close to each other. The second floor is doing most of the cooling, and you can see at this one point they probably just turned down the set point of the first floor unit perhaps, and then they all kind of came into line. Or they probably turned down the set point on both, and they all just came into line after that. So one of the questions you'll often face is, people do not trust heat pumps in a cold climate to heat a house. So let's look at equipment capacity. Did it actually meet set points and not have any comfort complaints on that front? So, like we said, we're using these heat pumps as a single source of heating in Massachusetts Zone 5A. Those two sites had design temperatures of plus or minus 2 Fahrenheit. The end-result testing that they did back in 2011 showed that the published specifications from the manufacturer are actually pretty reasonable. They do match output at those cold temperatures like they claim in their literature. So in the monitored data, there was no sign of low equipment capacity problems. That would be typically demonstrated by having a really long runtime at maximum capacity, and the indoor temperature is falling during cold temperatures. And there was no sign that I saw in any of this of those types of problems. There was very often loads of excess capacity available, well below the 2,000 watt draw point. This included the winter of 2013-2014, the so-called polar vortex, with way higher heating degree days than a typical winter in that climate. On those times when we saw temperatures declining indoors, this was typically because they either had the unit set at a low set point or they just had it plain old off for some reason, or some other malfunction or other control issue. That being said, one of the things that you have to put is what was the sizing of this equipment relative to the design load. So this table that I have here are the heating design loads for these various houses, the installed equipment capacity, and some of these are in brackets. So those are houses where there was first one head installed typically, and then there was a second one retrofitted afterwards down the road. I'll talk a bit more about that later. And this shows the oversizing factor. So this shows that for most of these houses, we're in the 150 to 200% oversized range, and in these houses, after the retrofit, in the 200% oversized range. So this is typically crazy oversizing for most conventional split systems or other units. But one of the things we'll point out is that oversizing provides loads of heating capacity at low ambient temperatures, as well as the fact that oversizing is not as big of a concern when we're talking about these mini-split heat pumps. Remember, they modulate well over their capacity range. So even though the maximum capacity is well oversized, it can ramp down much closer to the actual loads. So, this shows, the next topic we'll talk about is what Andrew talked about in great detail, was trying to space condition a two-story house from, 1 or 2 points of space conditioning. So, just as a little bit of background to reiterate what Andrew said, the idea of this is that we're taking advantage of a really low-load home, a super-insulated house, to simplify out the space conditioning system. The concept behind it is that because the outside shell lets heat out so slowly, you can think of the heat coming from the core and kind of filtering through all those interior partitions and floors. So as long as the heat is flowing through those interior partitions and doorways and interior gates, as fast as it's being lost through the exterior shell, you'll have a reasonable temperature inside that room. But if if the rate of heat loss through that exterior shell starts getting higher than what you can push through that interior partition or doorway, temperature starts to go down, you start to have some problems. Just to briefly summarize some of the previous work, this type of simplified space conditioning works better with smaller homes with a compact floor plan. Bedroom doors have a huge effect. With the door open, you often have, fine temperatures, but you shut the doors, you start seeing larger temperature differences, colder bedrooms in the winter. And the last thing is that a constant set point is definitely how you would want to run this. The more that you mess with the set point, the worse the variation in bedroom temperatures or those those other rooms is going to be. Now, for argument's sake, you can be completely safe and use that fully ducted system, but as Andrew pointed out, you will still see temperature variations away from your set point or between the rooms. But it's, at the very least, it is standard practice, so it is defensible in that respect. So, take that as you will. So, we did a similar type of analysis using ACA Manual RS, looking at the 4-degree temperature difference. We just did a simplified analysis here. We took the highest and lowest temperature in the house in the various points that we measured, took the difference between those 2 points, and plotted how many hours there were at those various temperatures, and just added up the number of hours. So you can see that there were a fair number of hours with 0 to 1 degree temperature difference between our various measurements. The majority was in the 1 to 2 degree range, then 2 to 3, and it kind of tails off from there. Also, this analysis omitted the bonus room and basements just because the basement, for instance, has no space conditioning in it, and it was not intended to be conditioned. The bonus room typically was left as an unfinished room, and some homeowners did finish it on their own. So what you can do is you can look at these bars, and you can also add them up for the percentage of the total. And we can see in this particular case, adding up the 0 to 1, 1 to 2, 2 to 3, 3 to 4. So that's the 4-degree difference. You can see that 96% of the hours in this particular house were below that 4-degree requirement. So we have a boatload of data to look at, 8 different houses, a variety of winter and summer operating conditions. The results varied all over the place. Sometimes we had great results, 80 to 90% of the time within that 4-degree band. Other ones, a lot worse. A lot more detail in this report, but many of these houses were under that 4-degree temperature band, and a couple of the houses were not analyzed because they were missing some of their key data. One interesting thing was that we looked at both the wintertime season performance as well as the summertime season performance. What we saw was that in the summer, the temperature variation was actually a little less than in the winter. The reason for this is that the temperature difference between indoor and outdoor is a lot lower in summertime design conditions versus wintertime design conditions. Just think about it, New England in the winter, 70 degrees versus 0 degrees, about 70-degree delta T. Summertime, 70 degrees versus 85, 90 degrees, 20-degree delta T. But one thing that I have to say is that these rooms had, all these houses had relatively low glazing ratios and low solar heat gains with those triple glazed windows. So your mileage will vary depending on which type of setup you have here and there. So that's very interesting. We have a bunch of cases where this tends to work great. So my thought, though, is that we don't learn too much from when it works. I think we learn a lot more when we look at pushing it until it fails. So that was some of the interesting sub-case studies that we looked at here on what were cases that did have problems, what caused that problems, how do we solve that problem. So one of the problems we had was houses with 2 stories and 1 mini-split heat pump. So this shows a couple of houses where these are on the smaller end of the production that they put out, in the 1,200 to 1,500 square foot range. So design loads are nice and small, 10 to 11 kBTU per hour, which is well within the design capacity of what these mini-split heat pumps can put out, even at design conditions. The other thing that the builder pointed out is he's been working with these types of mini-splits for a long time. He noticed that during the winter, typically the second floor unit barely runs. So what he was thinking is, look, the 1 mini-split should do it on these houses. Let's go ahead and run it that way. So good experiment. Let's try it. So the equipment was located on the first floor in each of these houses. So this shows some of the temperatures that we were seeing inside the house. Once again, to refresh, orange is outdoor temperature going from May through September. Indoor temperatures are shown here. Red is the first floor. These 2 blue lines that are overlapping each other are the second floor bedrooms. The green dotted is the stairwell, which is kind of halfway between the first floor and the second floor. So what we're seeing is that, the second floor temperatures are definitely running well warmer than the first floor. And you can also see that there's this real spike in outdoor temperature, and then the second floor really starts to heat up, well into the 80s and above, even though the first floor is chugging along nicely at below 70 degrees. Then, so basically the homeowners complained, we tried to tweak a bunch of things, but we finally gave up and added a heat pump, a mini-split on the second floor, and that immediately, you can see the immediate results. It's just pulled the second floor temperature right down to the comfort set point. So, one of the things to argue is, what about redistribution fans? What about things like that? That pull that cold air and push it into that bedroom. We actually had one of these redistribution fans, an exhaust fan pushing 40 CFM continuously from that first floor into one of the second floor bedrooms, and this actually is the performance that we were seeing. So a redistribution fan can help, but there's only so much it can do with that air. So it only can help you in an edge case versus a bad case. So what this tells to me clearly is that, warm air rises, cold air sinks. So, on using a single mini split on the first floor, that works great. Warm air rises, heats up the second floor. If you're doing it during the summertime, though, that cool air is just going to sit there as a lump on the first floor. Your second floor is going to start to rise like this. So this shows just a couple of images of how that second floor mini split was retrofitted. You can see the line set hide on the outside. It looks kind of like a rain gutter poking right through to the second floor unit, where they ran it inside the wall, inside the garage. So this thermal buoyancy thing, warm air rising, matters a whole lot for distribution, even in very airtight houses. All these houses test out in the 1 ACH50 range. Some of the previous wisdom has often been, like thermal stratification happens because you're leaking all your hot air out, so that's why the first floor is cold and the second floor is warm. Well, even at 1 ACH50, physics does happen, and you do end up with warm air rising. So if you're trying to do one mini split on 2 floors, choose heating or cooling and be prepared to kind of suffer for, during one of those seasons. Or either that or have a really big redistribution system to shove air all around the house. So, moving on to another topic. Another place where we saw problems were in a bonus room in one of the houses in East Hampton. So this shows the comfort complaint house that we were looking at. You can see the south orientation, big solar array on the roof, south face on that. So, just as a bit of background, this builder has been doing super insulated and super airtight houses with the two mini split house heads in loads of their houses without complaints. But a couple of complaints started to crop up in these Central Mass houses. This specific house was a custom house plan with a first floor bump out, a little bit more square footage, and they actually had the builder finish the bonus room over the garage as part of the initial package. So this shows another view of that house. The homeowner said that the downstairs temperatures were pretty darn even, and that they ran a constant set point on both the first floor and the second floor. So there was a bedroom at the front of the house that generally was the warmest, a few complaints there. The rear bedroom was colder than that, but the bonus room was actually very noticeably cold, 50 degrees in some of the really cold worst case conditions that they saw, with a 70 degree, 68 degree set point inside. So that shows the footprint of the bonus room. They also had cases where they accidentally left the garage door open and that bonus room got even colder. Not terribly surprising, just look at the geometry. They also had issues with the whole bedroom door open and closed thing. They said that, basically they have very strange schedules. Leaving a door open is not really something that will work with their lifestyle. So the first thought was, is this an airtightness problem? We retested that running at under 1 ACH50. Very nice and airtight. And it's definitely not a capacity problem. So that second floor had a 12,000 BTU per hour head. The design load at design winter conditions of the second floor is about 6,000. So we're well oversized in terms of capacity. What we're probably facing here is a failure for that heat to get from that core out into the bedrooms. So let's take a look at the floor plan and see what we have there. So this shows the plan of the second floor. The front is down towards the bottom of the house, so that shows the location of the mini split in the hallway of the second floor. That shows the front bedroom, with a attached, the bathroom attached to that suite. The master bedroom suite at the back of the house, which had some comfort issues, and the bonus room over the garage. So one of the things that's, to back up, it's kind of obvious what's going on probably to most of you. A bonus room over a garage is seeing very different conditions than a second floor bedroom that's over conditioned space. The bonus room has exterior conditions on 5 of the 6 sides of the cube, if you will, only one side condition, while these second floor bedrooms typically have, conditioned space below, conditioned space on the other 2 walls, so they do not have nearly as challenging conditions in terms of, the amount of heat that they are shedding. Another thing to point out is the ratio of interior to exterior walls. Remember what I was saying before about the rate of heat flowing out of a room versus what's going into it through partition walls and doorways. So you can see the ratio of the indoor walls to the outdoor walls for that front bedroom and versus that back bedroom. If you actually just ballpark out those ratios, it's like 2-to-1 versus 4-to-1. So it's not very surprising to me that that rear bedroom is slightly colder. You can also see that the rear bedroom has only has a little bit more in terms of glazing that will get some of the morning sun and the south-facing sun. If we want to do this type of analysis in more detail, Rob Aldrich from Stephen Winter did a very nice job of making just a spreadsheet of what are the relative heat losses, and you can just kind of calculate out, do what-if scenarios of what the temperature will be in the room with these various surface areas and U values. You add a transfer fan, how does the temperature change? You open the door, how does the temperature change? It's a quite elegant tool. So this shows a little bit of the monitored data from that comfort complaint house. What I'm showing here is the bedroom temperatures. The green one is the front bedroom that had few complaints. Blue is the rear bedroom, and yellow is the bonus room. Orange is the outdoor temperature. And so these dots down here show door closure states. These dots indicate hours when the door was predominantly closed for the bonus room, rear bedroom, and front bedroom. So what we can see from this is that over here they shut the rear bedroom door for a long period of time, and you can start to see the temperatures slide down there. They also shut the bonus room door, and it also starts dropping like a rock. And you can see in the steady state conditions with the door closed for a long period, outdoor temperatures in the freezing and below range. We're seeing 60-degree temperatures in the rear bedroom, 50-degree temperatures in the bonus room. Definitely well outside of the comfort range, to say the least. But then again, that being said, you pop open these doors, and all of a sudden these temperatures pop right back up. And they're definitely on the cooler side of where you would want to be, in the lower 60s, mid 60s range. But still, you can see what a huge effect door open and close state can have on these on the temperatures in these rooms. Yeah, so you can see many hours of these open door data, many hours within the 4-degree temperature range, but of course these are warmer temperature conditions above freezing range. All this being said, one thing that I want to point out is just because we had a comfort complaint in a bonus room does not mean a bonus room always causes a comfort complaint. This shows a different house located in one of the other subdivisions, and you can see that the dark blue, which is the bonus room, is definitely on the cooler side of all these rooms. But you can see it is pretty darn close to all the other bedrooms. It is not operating nearly in that way colder 50 to 60 degree range that we saw in those worst case scenarios in that comfort complaint house. Moving on to another topic. I said before that turning the temperature on off, set back the temperature down or up, or setbacks do not work very well with this type of a simplified system. We actually had a homeowner who did this type of operation in their house, so we could actually do comparisons how this house operated versus other houses. So first, as an example, I'm showing a house that ran the temperature at a constant set point, just straight flat out, straight flat temperature. Once again, outdoor temperature in orange, indoor temperatures, and mini-split energy use. You can see the temperatures are pretty close within a reasonable band, and that the mini-split is modulating up and down. And that basically, compare the mini-split energy use to the 2,000 watt peak load. We're at the, we peak out at about 1,000 watts. So, there's no big slug of heat, and this single point distribution works very well with this constant set point. This shows the house where they literally turn the mini-split on and off. The temperature is swinging, between 60 and 70 plus range for a lot of these things. The homeowner literally operated this unit saying, "I'm feeling cold. Are you feeling cold?" And turned the system on, ran it for a while, and then said, "Oh, I'm warm now," and turned it off. So you can see this kind of sawtooth behavior of swings, and you can also see that there are many hours. Oh, this shows like just a huge drop in temperature where it coasted down. But there are many hours where we're running at close to maximum capacity, 2,000 watts. Basically, when it slams into gear and needs to heat up the house, it's running like crazy. I'll just jump over this in terms of time, but one of the things I'll point out is that setbacks are often done usually to save energy. That's the concept behind that. That being said, if you super insulate a house and make it airtight, the temperature in the house drops very slowly during the off cycle, so there's less benefit from doing the setback. And in addition, these mini-split heat pumps operate at their worst efficiency state when they're trying to recover from a setback, and it's also typically going to be at the worst time of day, in the morning when it's very cold. So, let's take a look at how the results came out. So there's two houses that are of comparable size. That constant set point house, about 1,400 kilowatt hours of heating use over the winter. That on-off house, almost double that, 2,500, 2,600 kilowatt hours for that winter. So this on-off operation house was the worst outlier in terms of energy use per square foot, as well as in comparison with the model prediction, 160%. So just talking through a few last items. Actually, Gail or Heather, how much time do I have left? Oh, I'll just keep going for a little bit here.
Yeah, if you could wrap up in about 2 more minutes.
Okay, I'll just go overhead, split over these things, and just jump to my conclusions here. So, actually, two things. So one of the things I do want to point out is we actually did calculate out how many square feet per head we had. This is not meant as like some general guidance sizing information, but it's a worthwhile bit of information to realize. You can see that in most of these houses were in the 600 to 800, 900 square feet per head. In these comfort complaint houses, we were in the 1100, 1200. We added that second head, we're down to the 600 range per head. So just a little bit of things to think about when you're trying to design with a system like this. So further work that we're going to do with transformations, we'd like to possibly implement a different type of system for the second floor. They had those comfort complaints at East Hampton, and they had to change to a 3-to-1 indoor to outdoor mini split system on the second floor, basically one head per bedroom to ensure that these comfort complaints would not happen again. They ended up with more costly equipment and it's lower efficiency, and as a result they lost a really big energy efficiency incentive on each house. So what they're hoping to do is change to a small ducted air handler in the second floor hallway, a short duct run to each bedroom. There, we've solved the whole open door closed problem, and we're providing space conditioning to each bedroom as a result. This just shows a small image of the type of air handler that we're talking about. The problem is that this type of equipment does not quite exist yet, but I believe that it is coming online sometime in the next couple of months. So conclusions: mini split heat pumps can work very well as a single supply of heating in Zone 5A. Two-point heating works great in many cases, but the problem cases that we saw included problem geometries, that bonus room, exterior conditions on 5 sides, a single point in a 2-story house, that warm air rises problem, heating versus cooling, extended periods with the bedroom doors closed, and setbacks cycling your system on and off, and also worse energy efficiency as to boot. When we were pushing well north of 1,100 square feet per mini-split head, those were the cases where we did have problems for reference. If other people have data, I'd love to see it. Oversizing mini-split heads is probably a reasonable strategy for heating. And use of small air handlers on the second floor, the whole door open, door closed thing will no longer be a worry. So I'd be happy to switch this over to Heather and Gail to take questions, and I'd also like to thank our builder, Transformations Inc.
Okay, thank you to the panelists for these outstanding presentations. We have time now for a few questions. We already have some great questions from the audience, and you may submit additional questions through the question pane on your screen. The speakers will answer as many questions as time allows. The first few questions, we've got some questions here for Andrew. The first one is, under what circumstances would you recommend a production builder to explore the single point distribution strategy?
Yeah, this is Andrew. Yeah, so I guess what we more or less have concluded from our work is that, you know, if you have a floor plan with very simplified geometry, say a single-story ranch type of house, it's definitely worth investigating these single-point distribution strategies, whether it's a mini-split or something else. But whenever you have these convoluted floor plans with multiple floors and bedrooms, you know, I think both of these presentations show that, you know, that's still a difficult strategy or a difficult instance to condition towards.
Okay, and another question for Andrew. What effect would other strategies such as thermal mass or better solar shading have in the cold climate lab house, which saw solar heat gain drive many of the comfort problems?
Yeah, definitely. That was, you know, probably the biggest problem that we had in that lab house was that it had a lot of southern glazing, and in the winter, whenever you had the lower sun angles, on sunny days, some of those bedrooms overheated. And, you know, one strategy would just be to block that energy, but then we're actually missing potential passive solar heat that we could be using. So, you know, really what you should be doing in those cases is looking at the design of the layout of your house. And if you're going to have a lot of southern glazing, it really needs to be in a room or in a space that's able to passively mix with the rest of the house. And there might be other strategies such as increasing the thermal mass that could also help mitigate that effect. In this test house, it was an unfinished home. It was unoccupied. There were no objects, no beds, dressers, etc. in the house, and so that might have had some impact as well on the overheating that we saw.
Okay, and then another question, with increased velocity, how do you overcome the noise?
Yeah, I guess that's a question that people often ask, and something that we've found is that with the correct register, you don't have as much of a concern with noise. If you have a traditional register with a lot of fins, there might be potential for noise as you increase the velocity. But we've been doing a lot of work now with high velocity, small diameter, circular diffusers. And we've found that under normal operating conditions, they really don't make the noise that people have talked about. So I think you have to have the right register, and to some extent also the ductwork is going to have an impact on that. Certain types of ductwork also help to mute and muffle any whistling or any noise that might be generated.
Okay, and with multiple outdoor units and even more indoor fan coils, is a distributed mini-split strategy really simplified?
Yeah, I think that's an excellent question, and I guess what it comes down to is, we want to simplify the duct system as much as possible because, what we've generally found is that the ducts are where a lot of the problems occur. The air handler itself is a pretty, specific unit. They work or they don't work. Generally, there's not issues there, but the issue is with the distribution of the air. And, we think that actually having those individual units provides a more simple approach because you don't have to deal with a convoluted ductwork system. So, there are some drawbacks. Certainly it is more mechanical, separate units, but I think that in some regards it can be considered a simplified system.
Okay, and one more question for you, Andrew. What is the coldest temperature where the heat pumps work? Do they have backup electric strip heat, or what is the backup for the mini-splits if it is 5 degrees outside and the units can't keep up?
Yeah, the mini-splits that we had in the hot climate test house did not have a backup, and the temperature is never expected to get that cold in the hot climate. And I guess in the cold climate, the air handler was actually a centrally ducted air handler where we only had individual outlets. And in that case, we actually had a ground source heat pump supplying the heat. So the outdoor temperature, doesn't have that same impact on the ground source heat pump. And so maybe Coda could answer or speak more to that, as they have a lot of data from a cold climate with outdoor heat pumps.
Sure. This is Coda. I don't remember offhand the lowest temperatures that we saw, but just in general, the overview of the data we had did show, even in those really cold temperatures we saw in Western Mass in the winter of 2012-2013, no problems with capacity using the mini-split as the single source of heating.
Okay, and here are some more questions for Coda. The first one is, have you done any studies with mini-splits recessed in the walls trying to make them more aesthetically acceptable?
I've definitely heard about that concept of trying to get the mini-splits out of the way just so that they look a little bit better. Maybe they cover them up with a scrim. We have not actually done any of that type of research with transformations or with anybody else. My understanding is that the critical thing is to avoid blocking the return and avoid creating a pocket. I believe the return is on the top for most of these units. And also there's some risk of creating this kind of a pocket of air that gives you a false reading of what the inlet temperature might be. I'm sorry, I do not have more on that.
Okay, here's another question. Do required PSI exhaust fans have any influence on the effectiveness of these designs?
I'm sorry, I don't know if I understand that question. Do required PSI exhaust fans have it? Is that what the question is?
Yes, it is. Have any influence on the effectiveness of these designs? I'm sorry, I can't be more clear.
Okay, yeah. If the questioner would like to just clarify, I'd be happy to answer it.
Okay, all right. Well, in the meantime, we'll just go on to another question. The next one is, isn't stratification due to colder interior surfaces more than air infiltration?
My best understanding is that you can have a massive amount of stratification through air leakage just because the stack effect, warm air is trying to rise. It's going to leak out of the top and then come in. Replacement air is going to come in at the bottom. During the very cold wintertime conditions, that means you are introducing a lot of outdoor temperature air at the bottom of the building. You know, walking around these houses with an infrared camera, there was no sign of uneven temperatures, surface temperatures on the inside of the house. Basically, the second floor bedroom walls and ceilings were the same temperature as the first floor walls and floors.
Okay. And for mini split systems, is there a reason to consider HRV or ERV to keep adequate CO2 levels, especially in very tight houses like an ICS concrete house?
That's a great question. Just one of the focus of this presentation was space conditioning, not ventilation, but that is definitely a strong point to bring up in any of these houses where we're pushing energy efficiency, getting towards greater air tightness levels, and reducing air change with outside. A controlled mechanical ventilation system operating at a constant rate is definitely a key part of the whole package. HRVs and ERVs are a fantastic approach to do this. They're the most costly system, but the most energy efficient system hands down. That being said, transformations, they typically ran a mixture of HRVs in some of their houses as well as just exhaust fans in some of their other houses. People can challenge that exhaust fans do not provide very nice distributed ventilation. That is true, but it does provide some basic the lower end of ventilation there. Another point about HRVs and ERVs, I know this is probably getting too much into the weeds, but one of the traditional ways to fully duct an HRV is to drop the outside air into the bedrooms. This makes sense. You want the fresh air in these rooms where people are spending the most time. If you are considering a simplified distribution system, you probably want to do that with a bit of caution because remember, we're relying on that heat filtering from the core to the rooms to provide heating to those spaces. If we're creating an additional challenge by dumping cool or tempered, if you will, air into the bedrooms, you've made the job a little harder. So I believe Martin Holliday actually did a very nice Green Building Advisor column talking about rethinking HRV ducting for these simplified systems where they're actually exhausting, pulling from those bedrooms instead.
Okay, and one final question for you, Coda. When it comes to constant set point versus not, do you have any impression about what insulation or envelope leakage numbers would change the optimal strategy?
Oh, great. I'm calling it a great question because I'm kind of, I don't know where the tipping point is for what that necessarily will be. I know that the general guidance is the better your enclosure, the less worthwhile a setback is going to be. I know that the guidance that I've heard from other folks is that hitting the Energy Star level is probably reaching the point where setbacks become less and less worthwhile. The classic place where setbacks make a lot of sense are the leaky old sieve of an 1800s house, for sure. But I'm sorry I can't give better guidance than that, but my general impression is we're starting to hit the point. Probably if you're an energy geek like me, the stuff you're building day to day might be in that neighborhood.
Okay, thank you. That's all the time we have for questions today. Panelists, before we take our quick survey, do you have any additional or closing remarks you'd like to make before we close the webinar?
This is Andrew. I guess just thank you for your time. I hope that the data we presented and the things we discussed have gotten you thinking about some alternative strategies and aware of the challenges, and in some instances now that we're learning the advantages with these alternative strategies.
Yeah, this is Coda. Thank you very much for your participation. We appreciate it.
Okay, thank you again to our speakers. Now we'd like to ask our audience to answer 3 short questions about today's webinar. Your feedback will help us to know what we are doing well and where we can improve. The first question asks whether webinar content was useful and informative. To answer, click on the radio button right in the Go To Webinar panel. And the second question will ask about the effectiveness of our presenters. And the third question will ask whether the webinar met your expectations. Thank you for taking our survey. Stay tuned for the next Building America webinar on November 19th at 3 p.m. Eastern Time. This webinar will review Building America research results. Registration will be available soon on the Building America website. On behalf of the Building America program, I'd like to thank our expert panelists for their time today and to our attendees for participating in today's webinar. We've had a terrific audience and we appreciate your time. Please visit the Building America website to download a copy of the slides and learn more about the program. We also invite you to inform your colleagues about Building America resources and services. Have a great rest of your day, and we hope to see you again at future Building America events. This concludes our webinar.